My name is Robert Scheidegger, and today I'll be talking about the paper How to Escape Saddle Points Efficiently. By now, I assume that everyone has some exposure to the notion of gradient descent. Given a function f mapping a d-dimensional vector to a scalar value and a starting point x0, gradient descent determines the next point by descending the value along the gradient of the function f. Eta is defined as some step size which we can genuinely choose, and we multiply this by the gradient of the function, allowing us to control how fast we descend. We can generalize this to future time steps t, giving us a nice recursive definition that we can easily implement in code. The goal of gradient descent is then to find a first order stationary point where the gradient is 0. However, it is not clear how many iterations that this process will require, which is important if we want to solve this problem efficiently. Also, we can quickly observe that if we're trying to find a local minima, this condition is not sufficient because this allows us to also settle on saddle points because we are only checking the first order condition, which is not a desirable condition. We also note that here we often relax the exactness of the stationary point to be within some epsilon of the true zero gradient. Let's look at the gradient descent algorithm. So we say, well, we haven't converged. We perform the same gradient update step that we saw in the previous slides. Now, let's look at a variant of this algorithm that we'll discuss more in this paper called perturbed gradient descent. This has pretty much the same structure as our original algorithm, but we also include an additional perturbation condition, where when this is true, we randomly sample a point from a d-dimensional ball and add it to our current value. The motivating idea behind this is that if we are stuck at a saddle point, this perturbation allows us to stray away from it and seek a true local minima, or at least a second order stationary point. For non-convex functions, previous work tells us that gradient descent converges to an epsilon second order stationary point, more on this exact definition later, using generally weak assumptions of f. The purpose of this paper is to use two slightly stronger assumptions, namely Rho, Hessian, Lipschitz, and a strict saddle condition, to show that some version of perturbed gradient descent can actually find a true local minima. Importantly, they also show that the overhead required is only a polylog factor in dimension, which is important because many of the problems involving gradient descent have very high dimensionality. Previous papers have shown that gradient-based approaches can find second-order stationary points in polynomial number of iterations in D, which is good as a theoretical matter, but it is problematic for common use cases when D is prohibitively large. Other work has used the direct Hessian information to achieve truly dimension-free iteration results, but these are not really practical because they rely on computing the inverse of the full Hessian matrix on every iteration, which can be really expensive in practice. Other work has used the Hessian vector product information to achieve nearly dimension-free results by using an oracle that computes the product of the Hessian and some other vector, which can work well in some applications. This work proposes a variant of perturbed gradient descent that introduces a nearly dimension-free overhead to traditional gradient descent, which is comparable to the runtime of Karman and Ducci's Hessian vector product result. Let's look at a roadmap for what's ahead. This concludes the general introduction and overview of previous work in this area. We'll then move on to some background definitions that we need to get under our belt, followed by the main results of the paper, and then some brief takeaways summarizing the main findings. So without further ado, let's get started with the mathematical background. Let's start with the definition of an L-gradient Lipschitz, or equivalently L-smooth function. The terms are used interchangeably in this paper. A function is L-smooth if, for all pairs of points, the difference in gradient of each point is at most some constant L, times the distance between the points themselves. This gives us a nice bound that says that the gradient can't change too rapidly, which is a relatively common notion. We will also introduce the idea of alpha strongly convex, which is a stronger notion of convexity that says that the minimum eigenvalue of the Hessian at every point is at least some constant alpha. We notice that the first definition here gives us a relatively permissive smoothness guarantee, while the second guarantees that there's a unique stationary point for the function, as one would expect because this is an assumption about convexity. If we allow ourselves to use this notion of alpha strongly convex, then the literature gives us a quite strong convergence guarantee, which tells us that gradient descent will give us a solution within epsilon of the optimal solution in a logarithmic number of iterations from the starting point to the function value. This is a great result, but it only works for convex functions. And as we know from this class, we're generally interested in solutions to non-convex problems. So because of this, we sort of have a tendency to ignore this fact because the assumptions are just too strong for the problems that we're interested, and we seek some weaker assumptions that can help us solve non-convex problems. So next, we'll introduce this theorem, which I'll refer to as the gold standard, which we'll keep referring to in this presentation. So we'll see that for an L-smooth function f, the gradient descent will find an epsilon first-order stationary point in some number of iterations corresponding to the difference between the function value between our starting point and our optimal value. So this is a particularly useful result because in this, the number of iterations required is actually dimension-free. It doesn't require the dimension d of the function that we are dealing with, which is really nice for a lot of problems that we use gradient descent in, which are usually very highly dimensional. However, we note that this still has the possibility to find saddle points because it's purely a first-order condition. So in order to avoid saddle points, we intuitively probably need to use some stronger assumptions, but we still don't want to go anywhere close to assuming convexity because, again, we are focusing on these non-convex problems. And since the saddle points rely on some sort of Hessian information, we do likely need some sort of weak bound on the Hessian of our function, but again, not convexity. So to do this, we introduce the notion of row-Hessian-Lipschitz functions, which is a function that for any two points, the difference, the spectral norm of the difference of the Hessians of the function between these points is bounded by some constant rho times the distance between the points themselves. So similar to how the L-smooth condition gave us a bound on how fast the gradient can change, this gives us a bound on how fast the Hessian can change. And we note that this is still significantly weaker than convexity, meaning that we're generally okay with making this assumption. We can then define a second-order stationary point as follows for row-Lipschitz functions. So we say that it is a second-order stationary point if it is both first-order stationary and it's the minimum eigenvalue of the Hessian at the point is at least negative square root of rho epsilon. So this looks similar to convexity, but we note that since the right side is always negative, this is strictly much weaker, and they're sort of unrelated notions because of that. So let's take a broad look at the assumptions and results that we will relate in this paper. So I'll denote assumptions by ellipses and results with triangles. And so if we assume that a function f is L-smooth, then the gold standard tells us that we can get to a first-order stationary point in some fixed number of iterations. Then, on the other hand, if we make a really strong assumption, we assume that the function is alpha strongly convex, then we can get the very strong result of finding an actual minima in some logarithmic number of iterations. What we really want is something between these, something that is weaker than convexity but a little bit stronger than L-smooth functions. So we introduce, again, row-Hessian-Lipschitz. And with this and L-smooth, we will see in the main results that we were able to get a second-order stationary point with only a polylog factor in dimension overhead, which is significantly better than any reliance directly on dimension for large dimension sizes. And then we'll also see that if we make one more stronger assumption based on locality of saddle points, then we can actually combine this with the second order result to get an actual local minima for the function in a similar number of iterations. And note that this is a poly-logarithmic more than the first order convergence for traditional gradient descent. Now that we have the necessary background, let's move into the main results of the paper. We'll start by looking at the perturbed gradient descent, or PGD algorithm, in its full form. It starts by picking some values based on our input parameters, but the choice of such values isn't really that conceptually important for now, so we can think of this as just some sort of parameter generation step. Inside of our main gradient descent loop, there is first the main perturbation condition, which adds noise to our existing xt every some threshold of iterations, but only if the gradient is small, which is important, and we'll come back to that later. Then we have a termination condition, which sort of is a continual convergence check, which says that, well, if our value hasn't changed very much since our last noise addition, then we'll say that it has actually converged, and we will return that value. And then we follow that with our sort of standard gradient descent step. So we again note that the first part ensures that we are only adding periodic noise when the gradient is small, aka when we are near a saddle point. This is the only time when noise is really necessary. And the second condition ensures that we terminate if the function has not decreased by some f threshold value in a certain number of iterations. However, we might wonder, with these modifications, does this function still even converge? And we'll see that the key to showing convergence in a small number of steps is to look at what happens when we add our random noise from our d-dimensional ball. And we will see this more in a little bit. So Theorem 3 is the main result of the paper, which says that the PGD algorithm for an L-smooth and rho Hessian-Lipschitz function, we can choose some sort of initial parameters such that this algorithm finds an epsilon second-order stationary point with high probability in the following number of iterations. So we note that the left part of this is the number of iterations required for the sort of gold standard approach for general L-smooth functions that we saw before, and the right part is the additional overhead that this sort of algorithm requires for the perturbations, which is, again, a polylog factor that we talked about earlier. The entire formal proof of Theorem 3 spans many lemmas and arguments, so here I'll give a high-level overview of some of the new thinking and tools that led to this result. So a key observation is that for a given iterate xt in our algorithm, if we haven't yet converged, then we have basically two cases. Either the gradient of the function at that point is large, or the Hessian has some significant negative eigenvalue. Now, intuitively, if the gradient is large, then the regular gradient descent step should be doing most of the heavy lifting and making progress to, some second-order stationary point. This can be formalized with the following mathematical argument, which just says that we, at such a point, we make an improvement along our gradient, and we make some progress in finding our optimal function value. So now let's consider the other case. The idea is as follows. When adding a perturbation, we want to make progress away from the saddle point with high probability, since otherwise we get stuck. And after all, the entire point of this is to be able to efficiently avoid saddle points. Now, if we consider the perturbation to be a uniformly distributed d-dimensional ball centered at x, then we can characterize the volume of space into two distinct regions: a stuck region, where we will fail to escape the saddle point, and an escape region, where we do actually successfully escape it. And if the random perturbation gets out of the stuck region with high probability, then we can effectively escape these saddle points. Now, one of the tools we need to do this is to sort of have a width bound of our stuck region. Now, the proof of this is omitted, but the paper proves that the region of this stuck, or the size of the stuck region is at most delta R over 2 square root d. Now, note that width is sort of a term of art here because the surface is not necessarily flat, but this is the maximum distance between any 2 points in the stuck region along some axis, which you can sort of think as a width. So we can think about this reasonably well if we consider this perturbation region to be a ball in 3 space, where our origin is our starting point, and then we can see that our arbitrary sort of stuck region, visualized here, occupies some space around this point, where we want our random perturbations to be able to escape this region. So we can then use this intuition to put a bound on the size of the stuck region, and thus, because if we can bound the size, and because the ball is uniformly random, we have a bound on the actual probability of getting to the escape region. So we can represent the volume as an integral over the ball with an indicator variable for the stuck region, this I stuck here. And now we first notice that we can sort of rewrite this as an integral over the d minus 1 dimensional ball, where we have the additional component, not just the indicator variable, but sort of the dimension d component, or the width, along one of these dimensions. But we recall from earlier that we have a bound on this sort of width, so we can actually replace this value here. And now we can sort of collapse the other integral term, noticing that everything else is just constant values, which is just the volume of the d minus 1 dimensional ball centered at 0. So we then can sort of write out the probability that we escape as, you know, this region of the stuck region to the overall volume of the ball, and we can notice because this large term involved of this volume quotient is actually less than 1 based on how our parameters are chosen, that we are able to get to the escape region with probability at least 1 minus delta, which is the high probability factor that we are looking for. So we can actually escape the stuck region with high probability. So now we see that we've actually handled this case here. So with both cases handled, we have characterized everything in our space that is not converged. And so we conclude that our perturbed gradient descent algorithm can find an epsilon second order stationary point with only polylogarithmic overhead. So now we ask, well, can we do better? Can we actually use this to find some sort of local minimum? And the answer is yes, but we have to introduce a new assumption called the strict saddle property. So we say that a function f is theta gamma zeta strict saddle if for any x one of the following conditions hold. So either the gradient is large, it has a sufficiently negative eigenvalue, or the value x is zeta close to some optimal value, some optimal local minimum value. So we recall that based on our previous discussion, well, we can choose parameters theta and gamma in our PGD algorithm such that neither of these conditions is true for our final value, which means that if we do so, then we can ensure that the point of return is in this set, which must be true at the end of our algorithm of perturbed gradient descent. Therefore, we can see that for functions with the strict saddle property, PGD actually finds a true local minimum value. Now that we've gone through the main results of the paper, let's go through a couple key takeaways. For one, we'll note that because we used a stronger condition on f, notably Rowe, Hesch, and Lipschitz, we were able to get a stronger result, and then improved on that using this additional strict saddle assumption that allows us to exploit some properties and find actual local minima. then we're able to achieve a relatively simple algorithm, which is nearly dimension-free for finding local minima or epsilon second order stationary points of non-convex functions. And we'll note that this is sort of a first step towards a more general theory with strong, almost dimension-free guarantees for non-convex optimization. And so if there's one thing that you should sort of remember from this paper, I would say it is that this version of perturbed gradient descent can find an epsilon second order stationary point of a non-convex function f. Of course, there are the additional requirements in here, but in iterations poly-logarithmic in D with an additional epsilon term, which we expect.